Hey everyone, on this lecture we are going to study the stationary distribution in a Markov chain. A stationary distribution of a Markov chain is a probability distribution that remains unchanged in the Markov chain as time progresses. In other words, if a Markov chain reaches its stationary distribution, the probabilities of being in each state will no longer change with each time step. The stationary distribution is usually represented as a row vector pi, whose entries are probabilities that sum to 1. And moreover, a property of this stationary distribution is that given the transition matrix of the Markov chain P, then the stationary distribution is going to be equal to the stationary distribution multiplied by the transition matrix P. Now, an important aspect to note about the stationary distributions is that not all Markov chains have a unique stationary distribution, and some may not even have one at all. However, under certain conditions such as irreducibility and aperiodicity, a unique stationary distribution may exist for the Markov chain. Such conditions that we see here in blue we are going to cover later in the course. Let us now delve into how we can find a stationary distribution given a finite Markov chain. So given a Markov chain with its set of states, here we denote as K the cardinality of the set of states. So basically K is telling how many states we have in the Markov chain. Then we know that the transition matrix will be a square matrix K by K, so we have K rows and K columns. Now, to find a stationary distribution, this is very important. What we'll need to do is we'll have to solve a system of K unknowns with K equations plus an extra equation that basically represents that the sum of all of the elements of this row vector need to be 1 because it is a probability distribution. So let us come back to our example of writing a research paper, such example that we've seen on the previous lecture. And let us see how we can now find the stationary distribution of this Markov chain. Notice how we are given the transition probability matrix P, which is this matrix. We have 4 states. And so since we have 4 states, we ask the student how many equations we will have. Well, we will have 4 equations plus an extra equation that basically says that the elements of this vector of the stationary distribution need to sum 1. And so remember what we need to do here is we need to find pi such that pi is equal to pi multiplied by p. So we need to multiply this row vector with the transition matrix P. And this is precisely what we do. Notice how this is the stationary distribution representation. We have 1, 2, 3, 4 total unknowns. We have 4 unknowns because we have 4 states. So one could of course call these unknowns x, y, z and w, for instance, but normally we represent them as pi with a given index. But again, this is just an unknown that we need to find its value. So this row vector needs to be equal to this row vector multiplied by the transition matrix. So here it is very important to remember how we can multiply matrices. We assume each student already knows this operation and such operation. Nevertheless, a quick recall, remember, if we have a matrix A, let us suppose the dimensions of this is n times m, so basically A has n rows and m columns. Let us suppose B has these dimensions, so it has p rows and q columns. Now a general rule to be able to multiply these matrices is that the number of columns of the first matrix needs to be equal to the number of rows of the second matrix. So here the condition is that m needs to be equal to p, and moreover, the dimensions of the resulting matrix, let us just call R, is going to be n by q. So the resulting matrix will basically have n rows and a total of q columns, right? This is basically a recall of the condition to be able to multiply matrices. Now let us delve into how we multiply them. Suppose that this matrix A is this matrix in here, in which we can see it is a matrix that is 3 by 2. We have 3 rows and we have 2 columns. And then we have this matrix B, which we can see it is a matrix 2 by 4. We have 2 rows and 4 columns. we can see how the condition is verified. The number of columns of the first matrix is equal to the number of rows of the second matrix, and the resulting matrix, the one that is the result after multiplying these two matrices, is going to be a matrix with 3 rows and 4 columns. Now, to compute this matrix, it is very simple. At the very beginning, we take the first row of the first matrix and the first column of the second matrix, and we multiply using the scalar product of these two vectors. So here 1 multiplied by 5 is 5, plus, because it is the scalar product, 3 multiplied by 1, which is 3. So 5 plus 3, this gives us 8. And so 8 is the element at the first row and first column of the resulting matrix, because it is the element that we use to compute with the first row of the first matrix with the first column of the second matrix. And so this gives us 8, then we do the same thing, but now with the first row of the first matrix with the second row with the second matrix. So this gives us the scalar product of these two vectors. 1 times 8 is 8, plus 3 times 2 is 6. 8 plus 6 gives us 14. So this gives the element at the first row and second column of the resulting matrix, because it is an element that we used to compute using the first row and second column of the first matrix and second matrix respectively. And so this gives us 14. The same if we continue here, this scalar product is going to be 18, and then this scalar product is going to be 7, and then we do the same process but now with the second row of the first matrix, and we do now the first column of the second matrix. This scalar product gives us 27, and so on and so forth, until we have the complete resulting matrix. Notice that in order to find the stationary distributions, we need to be able to multiply matrices, because it is in the matrix multiplication in which we here express the system of equations. Notice how this first unknown, the unknown p sub r, is nothing but the expression of the scalar product in which we multiply this row vector, this unique row that we have, with the first column of the second matrix here, with the transition matrix. So this gives us pi sub r multiplied by 0.5. This gives us 0.5 multiplied by pi sub r, plus 0.2 multiplied by pi sub w, plus finally here we see we multiply pi sub e. Okay, we multiplied by 0.1. This gives us 0.1 multiplied by pi sub e. Notice that the last multiplication, basically it is a 0 multiplied by pi sub s, so we don't even need to put it in here because it is 0. This is the first element of the resulting matrix, the matrix that is the result of multiplying this row vector by this matrix. So we have this resulting matrix, this resulting row vector. So this is the first element. Then the second element is basically multiplying this row vector, the first row of this matrix. We only have one row, with the second column of this second matrix in here. Okay, so this will give us the element at row 1 and column 2, which is this second element. So here we do this scalar product. This is basically pi sub r multiplied by 0.3, as we can see here, plus pi sub w multiplied by 0.5, as we see here, plus pi sub e multiplied by 0.3, and finally plus pi sub s multiplied by 0.2. So this is basically the expression for the unknown pi sub w, and the same for the third element, for the third unknown pi sub e, and the last element, the last unknown pi sub s, right? So we have this system of equations, and additionally the last equation of this system, because notice that if we have k states, we'll have a system of equations of k unknowns with k equations plus an extra equation that basically says that the sum of all of these elements need to be 1, because this is a probability distribution. So given this system of equations, and so we solve this system of equations with, for instance, substitution or other system solving methods, and we will obtain this solution for the unknowns. Once we have all of the unknowns, we have the stationary distribution. So let us now recap the main points of stationary distributions and close this lecture presenting new ideas for the following lectures. First of all, a Markov chain with k states and transition matrix P has a set of k plus 1 stationary equations with k unknowns from pi sub I to pi sub k, Such a stationary distribution is given by this equation together with the probability distribution enclosement, such that if we sum the values of all the unknowns, this needs to be equal to 1. Moreover, linear algebra tells us that such a system either has a unique solution or infinitely many solutions. And what we want is a unique stationary distribution. Having a unique stationary distribution is desirable for several reasons. First of all, a unique stationary distribution implies that the long-term behavior of the Markov chain is well-defined and predictable. Also for conversions, if a Markov chain possesses a unique stationary distribution, then this suggests that regardless of the initial state, the chain will eventually converge to that unique distribution, as the number of steps or time approaches infinity. This property simplifies analysis and modeling, as it provides assurance that the system will stabilize over time. So since we want this unique stationary distribution, we will see the conditions that must hold for the Markov chain to have a unique stationary distribution. We are going to see such conditions on the following lectures.